Today, we are going to get into the core of this storage. First of all, when we talk about storage for databases, when we talk about databases storage, we are talking about disk-oriented logical disk storage. Because as we all know, that the memory is a volatile system. So the data in memory, if the computer is powered down, the data will not be retained. So in order to prevent the data from being lost after a power failure, we assume that all of the databases that are stored are in locations that are non-volatile. And then we are going to build this on the disk database accordingly. Most of the databases that we talk about are geared towards storage logical, that's disk-based storage logic. And the DBMS, what we call the database management system, and its component management, is actually dealing with the non-volatile data and exchanges between volatile storage. And that's mainly from the hard disk to the memory, and then from memory to a part of CPU, for example. And then it goes from storage to computation. So these components are mainly managing my data. How it's organized on the hard drive, how it's organized on the hard drive, or how it's scheduled into memory. The how is organized in memory and then feeding into CPU or some other kind of computing unit or GPU or something like that. So first of all, let's be clear about one thing. If a database is very fast, it may have a lot of limitations, which are at a memory level and not at the hard disk level. Because as you know, from the memory to the hard disk, the I/O is a huge bottleneck. And so our management is also geared towards the logical management of the disk. How to fully utilize the memory, including taking full advantage of these scheduling features and caching mechanisms to accelerate the process and make the database more robust, such as failure tolerance, fault tolerance, and competency control. These are the problems faced by databases. The problems with storage and need to solve them. Let's look at the main storage hierarchies. Now, the common storage hierarchies that are used, we basically put it through 7 levels. That is, at the top of the hierarchy, the CPU registries, and the CPU cache, and DRAM memory. They are all actually volatile memory, which means that if you cut the power supply, the data is lost. And this volatile storage, which supports, for example, bytes and fast random access, that means that the program can jump to any byte address to process data there. So it's going to access it faster. It's called memory. And the next level is hard disk, like SSD, HDD, and network storage. They are slow. The smaller I/O throughput means that they are slower to read, but it's bigger in size and cheaper. So the closer you get to the CPU and the memory, it's actually faster and smaller, but it's more expensive. However, this non-volatile storage device, as I said earlier, that I don't need to provide persistent power to keep the data stored. Like my computer, I have on my hard disk. This file is saved at less power. I shut down my computer, and when I turn it back on the next day, when the system rebooted, the file was still there. We wouldn't say because I lost power that all the files were gone. It's usually in blocks or pages, and then it goes to this corresponding storage. In the case of non-volatile storage, in terms of the design of the non-volatile storage, the sequential access is very fast. So we have very fast sequential access, and I'm going to talk about why sequential access is very fast. And then we call it a hard disk. But actually, in this storage, we don't make a distinction between a solid-state drive and a mechanical drive. How do we do that? So we may think of it as a disk or a hard drive. So when they are comparing the 6 different levels, and then we compare them in terms of access speed. And what kind of differentiation is that? Here is a comparison. That is, if you open the cache in level 1 and level 2, it's about 0.5 nanoseconds and 7 nanoseconds. In DRAM, in memory, it's about 100 nanoseconds of access time. In SSD, it's about 150,000 nanoseconds, and then HDD, the network storage, and then the last disk after that. This nanosecond concept, you might have some doubts on that. Let's discuss it in another way. If level 1 cache is 1 second, then the level 2 level of the cache is about 14 times of that. So it's 14 seconds. And the memory part is about 200 seconds. The SSD is about 3.4 days. And then the HDD, so the mechanical hard disk is about 33 weeks. That's about 2/3 of a year. If you're talking about network storage, that's about 22.8 months. That's close to 2 years. And then if it's one of these old tapes or this tape-based storage, that's about 67 years. And you can visualize it like this. 1 second from this, and then 67 years, that's the situation. The case is that it's going to be bigger and slower, but cheaper. From this volatile storage to this non-volatile storage. The top one is this volatile one, and the bottom one is non-volatile. So there is also some fun fact. In the United States in 2018, a US manufacturer of storage, they actually invented a product called NVDIMM, which is a non-volatile memory. This non-volatile memory is something like this, and there is Micron logo. It's actually a very common one, a very common design for volatile memory. But it got non-volatile particles integrated into memory. And that's what it's trying to do at the memory level. It guarantees both the access speed of the memory and its addressed in bytes, but also have non-volatile particles, which is to make sure that when there's a power cut, the data is retained. So it's a blend of volatile and non-volatile. But we're not going to get into the details today. Let's just say, in the spirit of memory, it's the volatile storage, and then disk is non-volatile storage. And then the main conflict we are dealing with is volatile storage. The speed of non-volatile storage and the balance between capacity and cost. In this particular case, using volatile memory could be costly. In fact, even now, 3 years later, this product hasn't become the mainstream yet in the industry. Anyway, thank you. That'll be it for today's section. And CnosDB is alive now, and you can join our Discord channel on the internet